All right, so let's go over the discussion question from module number 2. So two parts to this. So it's a lot like something you had to do for module 1. Basically, I am giving you some conditions that you have to meet for a function, and aside from that, you have a lot of freedom. So again, your answer might not look too much like mine, but so let's start dealing with the requirements first. So I know that the average rate of change over this interval from -3 to 0 is -2. So what does that mean? Basically, for every unit I travel in the x direction to the right, I'm going to travel downwards in the y direction by 2. So let me kind of rewrite what that says. So delta y over delta x equals -2. So again, to be clear, I'm using this capital delta to stand for a change in something. So what are we also told? We're also told that, how long this interval is. So what is my delta x? Basically, it's going to be however far apart the x values of the interval are. So 3. So what does that mean my change in y has to be over that interval? So delta y over 3 equals -2. That means that delta y equals -6. So basically, here's what I know for this first part of this bullet. Over a span of 3 x units, I need to increase by 6 y units. So let's just do this. Let's start at -3, 3. And then from -3 to 0, I have to decrease by 6. So basically, that's going to put me here. So again, you don't have to begin and end at those two places. I mean, you probably want to be close to this if you want to stay on this plot. But that's what I'm going to stick with. So this point right here will be -3, 3, and this point right here will be 0, -3. Okay, so I know those 2 points are going to be on my graph. Now I want to basically do the same kind of calculation for the other interval. So from 1 to 3. So make a note here. This right here is from -3 to 0. I want to do a similar calculation from, 1 to 3? So from 1 to 3, I want delta y over delta x to be what? 0.5. My change in x total is going to be 3 minus 1, which is 2, which means my delta y over 2 is going to be 0.5, which means my delta y is going to be 1. So basically, from 0 to 2, I want to increase by 1 unit. So let's decide where we want to begin. So can truly choose anything. I'll go from -2. I marked the wrong, didn't I? So I want to go from -2 to -1. So basically, I have graphed 4 points that I would like to put on my graph. So I believe that those 4 points, that's going to be as much as I can do to handle that first bullet. So that's average rate of change. So average rate of change comes from, calculating slope the way you have been doing for years. So I have some change in y value. I have some change in x value. The change in x value cannot be 0. I have to have 2 points, 2 distinct points. That's how I calculate average rate of change. Bullet number 2 talks about the instantaneous rate of change. So this is the big new idea when it comes to derivatives. I would like to talk about the rate of change at a single point, not 2 points. So I want the instantaneous rate of change at -1 to be -1. So let's figure out what that looks like. Lots of different kinds of language you've heard to talk about derivatives, and one of those is probably slope of a tangent line. So when we talk about slope of a tangent line, we're talking about if we were to make, have a line that touches a curve at only one place, what the slope would be of that line. So I want this slope to be -1, and I want slope to be, or I want this to take place at -1. So what's that slope going to look like? It's going to look something like this, right? If I could draw it as accurately as I wanted to. So I'm not sure that's where the point is going to go through, but maybe it is. And what else do I want? I want the instantaneous rate of change at 2 to be +1. So let's do this. Let's say I want this, again, the location I am picking is not the place it has to be. You have a lot of freedom here. So I think, so from the first bullet, I decided where a bunch of points were. From the second bullet, I figure out what a couple of slopes and tangent lines that I wanted to use were. And now what remains is for me to basically connect. I don't want to say connect the dots because they're not all dots, but so the average rate of change, I have a lot of leeway here. Maybe this has a really steep decline here. And all that really matters is that when I get to x equals -1, I have a tangent line that sort of fits like that. As I move from left to right, I remember that I wanted my average rate of change from -3 to 0 to be -2. And one thing I want to point out is that's part of the reason I'm drawing this curve so strangely is because it does not, for average rate of change, I don't care what happens in between -3 and 0. The average rate of change is only governed by what happens, at the end points of that interval. From x equals -3 to x equals 0, I want to have my function decrease by 6 total units. Kind of took a strange approach to make that happen, but it did do it. So from there, I can continue my graph to the right. Maybe going to the right, I'll do things a little more straightforward. In fact, I am going to get rid of this tangent thing right here. And let's just, again, I still want to have a slope of 1 at x equals 2, but maybe I'll put that here. So tangent line or tangent slope of 1, and then come here. So again, your graph would look a lot different from this, but I believe that I have met every requirement that's on here. So let's go ahead and look at the second part of this. All right, so moving on to part B of this question. So let's handle the requirements. So we have G3 minus G of -2 over 5. Now, it might seem arbitrary at first why the denominator is 5. It's not. The reason there's a 5 in the denominator is this. We are really looking at this idea. If 3 and -2, if I figure out their difference, how far apart those two x values are, that is 5. So what I'm really looking at here is a slope calculation across 2 different points. Or in other words, I'm looking at the average rate of change on this interval. -2, 3. And I can say something very similar for my other interval. So again, it's not arbitrary that the denominator is 2. That is how far apart -1 and 1 are. So my average rate of change on the interval -1 to 1 -1. So now let's see how we can translate those two pieces of information to a graph. So from x equals -2 to x equals 3, I have a average rate of change of 0, which means over that change in x, I'm going to have 0 change in y, which means whatever value I decide to choose for, at x equals -2, whatever y value I choose, I'm going to have the same y value at x equals 3. So that's how we deal with the average interchange across the interval -2, 3. How about over the interval -1, 1? Well, the average interchange there is -1. So let's talk about change in y's and change in x's again. We know that this average interchange is -1. But what is the total change in x? The total change in x is going to come from how wide the interval is. So how far apart those x values at the endpoints are. So that's 2. So if I solve for delta y here, that's going to give me a total change in -2. So across this interval, so from -1, and let's just say I'll choose the point -1, 0. Where do I need to be at x equals -1? Well, I need to be 2 units below that. So that's going to put me at the point 1, -2. And again, there's no one way to do this correctly. No one way to kind of structure this or to kind of decide where all these points are. So again, your experience on this question might vary. Not just the way your final product looks, but the way you decide to kind of organize it and structure it and put the pieces together. So the average rate of change helps me put those 4 points on here. So what about the second bullet? So I think I'm going to check off the first bullet. Now, what does this mean? What does g prime of 2 equals 1 mean? So g is a function that I'm going to graph. G prime, the little apostrophe there, we pronounce that prime, just a reminder. That refers to another function, specifically the derivative of g. So what does it mean if g prime of 2 equals 1? Well, that means that the slope of a tangent line at this location, at this x value, is 1. So we talked about, in the last example, we had slopes of 1. And that's going to kind of look like this. Again, we might not actually place it there, but maybe we will. Let's see when we come to it. And then we can also do g prime of -1 equals 0. We just talked about what a slope of 0 means. So we just talked about it with the first bullet. We talked about an average rate of change being 0. This is referring to the IROC, or instantaneous rate of change. The instantaneous rate of change equals 0. That means the slope of the tangent line is 0. And just like with the average rate of change, a slope of 0 means that we have a horizontal line. From our previous part, we already designated that this function is good. The graph of this function is going to go through -1, 0. And now we've decided that this is going to have a horizontal tangent line. So I think based on everything we've done so far, we have enough information to graph this. So I have 4 points, and I have 2 locations that are going to have prescribed slopes. So I want to have a slope of 0 at this point here. Maybe it comes back up, not that it has to. I do want to reach this point here. And as I continue on here, I want to make sure that I have a tangent slope of 1. So I'm going to try to make that happen. And then I want to end at this point here. And really, it doesn't matter what goes on after the endpoints here. But if we look at all of our different bullets, all of our requirements should have been met. So we should have all of our average rates of change, or our 2 average rates of change should be respected, and our 2 instantaneous rates of change should be identical. Again, your graphs your graph is very likely to look completely different, and that's okay. All right, hope this makes sense.